This is insect-inspired foot design for robotic locomotion across irregular terrain. In legged animals, feet play a vital role in stability, traction, balance, weight distribution, kinematics, and dynamics. However, many legged robots lack specialized foot designs and instead rely on simplified stubs as feet. This creates many problems when navigating on complex terrain. This project aims to design a robotic foot that maintains simple robotic controls while improving locomotion by passively engaging with the substrate and increasing contact area compared to simplified designs. The design is inspired by the anatomy of insect legs. In insects, the movement of the tarsus or feet is controlled by a single muscle which is located higher up on the leg. When this muscle contracts, a tendon-like structure called the apodeme pulls on the tarsal segments, causing them to rotate downwards. The muscle has no antagonist, and elastic forces in the structure of the tarsus passively disengage the tarsal segments when the muscle is relaxed. The design itself includes a pad located on the bottom of the foot. When pushed upwards by the weight of the robot's body, the pad pushes on the lever sticking out from the claw segment and causes it to engage by rotating downwards. When no force is applied to the pad, elastic forces in the spring, which are connected to the claw via a string, cause the claw to return to its disengaged position. The main components were 3D printed from mark-forged onyx. Aluminum rods and Kevlar string were also used. The pieces were finally bolted together to create the final assembly. For testing, a 500-gram weight was placed on a specially designed slot on the foot to simulate the robot's weight. A force gauge was then inserted in a slot on the back of the foot and pulled horizontally. 4 different terrains were selected for testing. These include grass, mulch, pebbles, and mud. Clawed and non-clawed variants of the design were used on each terrain. The maximum force was recorded for 10 trials for each combination of terrain and design variant. The maximum horizontal force from the 10 trials was averaged, and a comparison was made between the clawed and non-clawed variant on each terrain type. The percent increase in maximum horizontal force of the clawed design compared to the non-clawed design was calculated. The results demonstrate an increase in maximum horizontal force across all terrain types. The grass terrain demonstrated the most pronounced increase, while the lowest increase occurred on mulch. These findings suggest that the clawed design enhances locomotion by improving substrate adhesion across varied complex terrains. The design should be modified to make it attachable to a walking robot for further testing. Claw variations could be designed and tested to compare performance on each terrain. Further design refinement is required to improve assembly, appearance, and minimize exposed parts.